Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 12 on the idea of density. All right, so let's jump right into it. Density is a very important idea, all right? And we're first going to talk about population density, but just density in general. One of the most important ideas in science and other fields is that of density. Now, density can be thought of as a measurement of how much of something lies within a unit area or a unit volume, right? How much lies within a square meter or a cubic yard or something like that. Now that something could be mass, it could be weight, it could be really anything at all. Often it can be people or animals or some other type of population, all right? So we're going to start off by taking a look at population density. Exercise number 1. The approximate population for Chicago, Miami, and Seattle in 2023 is shown in the table below, along with the area of each city in square miles. Letter A. Calculate how many people per square mile live in each city. This is called its population density. Round to the nearest whole number. All right, so again, this is really kind of an average thing, right? So I've got Chicago, right? It's got a population of 2,694,000, all right? And it's got an area of 227 square miles. So the idea is with population density is I want to know how many people live in 1 square mile. I know how many people live in 227 square miles. I want to know how many people live in 1 square mile. And I do that by just using division, because that's what division tells me, right? If I've got a certain number of candy bars and I divide them up amongst, bowls, right? Like 5 bowls, I'm going to figure out how many candy bars I have per bowl. Here, I'm going to figure out how many people I have per square mile. So let's use D for density. And maybe we'll do D sub C for Chicago, and that's going to be 2,694,000 people. Chicago's a big city. Divided by 227 square miles. And let's find out how many people live in each square mile in Chicago. Just got to be careful. 2,694,000 divided by 227. And I did it again. There we go. All right, that's going to be 11,868. And again, to be very clear, right, there are units. That's people per square mile. Now, by the way, if that seems like a lot to you, I totally get it, right? Almost 12,000 people live in every square mile in Chicago. Keep in mind, though, of course, Chicago's a city, so many people live in apartment complexes, right? So they're kind of being stacked vertically on top of each other. And on top of that, a square mile is actually quite a large amount of area. So here's what I'd like you to do. I'd like you to pause the video right now and figure out what the population density is in Miami and in Seattle. Take a moment to do that. All right, well, Miami has a much smaller population than Chicago, still a big city at 462,000, but a much smaller area, 36 square miles. So let's figure out the density of Miami, right? That's going to be 462,000 people, all divided by 36 square miles. And let's figure out what we have there. 462, 462. I got a little bit faster than the calculator could handle. Ah, nuts. Oh, no. No. We don't like that. Again. There we go. 460,000 divided by 36. This time I'll be good about remembering to hit that. And that's going to be 12,833 people per square mile. And right away, by the way, before we move on and take a look at Seattle, we can already tell that in a certain sense, Miami is more crowded than Chicago, right? There are more people living in a square mile in Miami than there are in Chicago, even though Chicago has got a much larger population than Miami. All right, and finally, Let me move this out of the way. Let's take a look at the population density of Seattle. That's going to be 745,000, right? Larger than Miami, smaller than Chicago, divided by 84 square miles. I'm really hoping my calculator works for me this time. 745, 1, 2, 3. Thank you, calculator, divided by 84. And we end up getting 8,869 people per square mile. And so we can actually see from this that Seattle, right, is the least crowded of the three cities, right? There are only 8,869 people that live in a square mile versus Miami, 12,833 people that live in a square mile. Okay, it's kind of a measurement of how crowded something is. Now, given that, take a look at letter B. How many more people live in a square mile in the most densely populated city compared to the least densely populated? Well, conveniently enough, here's the most densely populated, and here's the least, right? This is the most densely populated, and this is the least. So, see if you can figure out the answer to letter B. All right, well, we just have to subtract these two, right? If we want to know how many more, we subtract. So 12,833 minus 8,869. And we're going to find that there are 3,964 more people per square mile. Seems like a lot to me. Miami must be a crowded, crowded place to live. All right, so population density is simple, right? It's how many of something, very often people, but it doesn't have to be people. It's how much of something or how many of something per square unit of area. In this case, it was per square mile because that's how, in our country, we measure areas of cities typically, not per square meter or anything like that. Although you certainly could do that. You could look at how many people live per square meter or per square foot. Although, boy, if we're talking about the number of people who live per square foot, that's a very small amount of area to live in. All right, let's do a little bit more with population density. Let's take a look at exercise number 2. Shayna is planting 400 sunflower plants in a garden. She is surrounding the garden with 30 meters of fencing. Shayna is debating between a garden that is an equilateral triangle and one that is a circle. Assuming Shayna uses all the fencing to surround each type of garden, then in letter A, we want to calculate the maximum area Shayna can enclose for each shape, round to the nearest tenth of a square meter. All right, so in other words, right, obviously, if we're going to eventually calculate the density of the sunflowers, right, how many sunflowers per square meter, right, then we need to know the areas of these two gardens. Now, this is kind of interesting, right? Because the only thing I know about these two gardens is their perimeter, right? The perimeter of this thing is 30 meters, and I guess not the perimeter, but the circumference of that circle is 30 meters. So let me write that down right here. Here the perimeter will be 30 meters, and here the circumference will be 30 meters. Now, believe it or not, based on that, you should be able to figure out what the area of each one of these is, but it's going to take a little bit of work. So I'd like you to pause the video now and see if you can figure out what the area of each one of these shapes are, given the fact that the perimeter and circumference are 30 meters. All right, well, the equilateral triangle, interestingly enough, will be the easiest one, right? And the reason for that is given the fact that it is a 30-meter perimeter, its side lengths must be 10 meters each. Awesome. But we also know that equilateral triangles have angles that are all 60 degrees each. And now we can use the area formula for a triangle that depends on sides and an angle in between them. So the area of the triangle is going to be 1/2 times 10 times 10 times the sine of 60 degrees. I want that to the nearest square meter, so let's figure that out. Let's get rid of all of that. I'm just going to do 0.5, or I'm going to try to do 0.5. Nope, again. And on the other hand, I think I'm going to do the fraction since my 0.5 is not behaving for me. I'm going to do 1/2 times 10 times 10 times the sine of 60 degrees. And that's going to be an area of 43 square meters. Oh no, to the nearest tenth of a square meter. My apologies, nearest tenth. So that's going to be 43.3 square meters. All right. Now the circle's harder, right? We know the area formula for a circle, right? The area for a circle is pi r squared. The problem is we don't know what the radius is. So that's our first stop along our road to figuring out what the area of the circle is. Now we do know that 2 pi times the radius is going to be the circumference, which is 30, right? If we divide both sides by 2 pi, right, then we find out what our radius of the circle is. So let's do that really quick. I'm going to use my fraction again just to make sure that I properly divide by 2 pi. All right, we've got 30 divided by 2 pi. I hit enter, and the radius of my circle is going to be 4.775 meters, let's say. And that's all I'll need now to figure out the area. The area of the circle is going to be pi times 4.775 squared. So let's just do pi. And I think I'll do times my answer squared on my calculator. And that gives me 71.6 square meters. By the way, I just want to note something right away because this is kind of cool. Look at how much more area we get with the circle than the triangle. And keep in mind that the path that bounds both of them is exactly the same length. So if you want to get the most area for a given perimeter / circumference, the circle is always the winner. Okay, now let's take a look at letter B. Using A, calculate the sunflower density for each garden. Round your answers to the nearest tenth of a sunflower per square meter. All right, so this is simple enough. How many sunflowers did we have? I think it was 400, right? We have 400 sunflowers. We want to divide in one case by 43.3 square meters, in the other case by 71.6 square meters to find out how many sunflowers will get planted per square meter of area. Pause the video now and find both of those densities. All right, well, let's do it. So for the density for the triangle, all right, we are going to have the 400 sunflowers divided by its area, which is 43.3. And that's going to be messy, but that's why we have our calculator. 400 divided by 43.3. And we're going to get 9.2 sunflowers per square meter. Now, a square meter is pretty big, so don't be too worried about that. The density of the circle is going to be 400 sunflowers divided by 71.6. And let's figure out what that is. And that's going to be 5.6 sunflowers per square meter. Awesome, right? And let's take a look at the last problem. Which shape allows Shayna to spread the sunflowers out more? Explain. All right, well, this should be pretty obvious, but why don't you go ahead and pause the video and give me your answer. Well, you could really say two things. Well, number one, you got to say this, the circle, right? But you could make two different arguments. You could either say the circle simply because it's got a greater area, right? I mean, without even knowing anything about density, the plain fact is because there's more area for the circle than for the equilateral triangle, we can simply spread our sunflowers out more. Or you could say the circle because it's got a lower density, right? The lower the density of anything, whether it's population, sunflowers, or anything else, the more spread out the quantity is that you've got within the unit area or the unit volume. All right, the more spread out it is. So it's the circle, you know, and I'm gonna go to the density argument, the circle, because it results in a lower density. And again, it would be completely okay to say the circle because it's got the greater area. That's also completely okay. Now, everything that we've looked at so far, right, have been population densities. But we can also look at density based on volume. Now, density is often used on a volume basis, far more than on an area basis. And we have seen densities arise in many of the volume problems already, right? We had a problem with I think it was like a grain silo or something, where we literally said that the corn can be packed in at a density of something like 16 pounds per cubic foot or something like that, all right? Now, one of the most common volumetric densities is what's called mass density. And in all likelihood, you've actually already worked with mass density before in some of your science classes. And it's really simple, right? It's simply the mass of an object divided by its volume, right? So how much mass is in a cubic centimeter, or how much mass is in a cubic inch, or how much mass is in a cubic foot, or something like that. So let's take a look at exercise number 3. Given each object below, along with its mass, calculate its mass density to the nearest hundredth of a gram per cubic centimeter. All right, so again, anytime you see something like gram per cubic centimeter, you know that you're dividing grams by cubic centimeters, so you're dividing mass by volume. Now we're given the mass, 785 grams in letter A. What we're not given in each one of these problems is the volume. So that's what we have to actually calculate first, then we calculate the actual density. All right, so let's do that. In letter A, right, the volume of that prism is going to be 8 centimeters times 5 centimeters times 3 centimeters. Let's figure out what the volume of our prism is. Let me clear all this out. 8 times 5 times 3. And that's going to be a volume of 120 cubic centimeters. Awesome, great. Now, all I have to do is take my weight and divide it by my volume. I'm sorry, take my mass and divide it by my volume. Density is going to be mass divided by volume. That's going to be 785 grams divided by 120 cubic centimeters. And I actually think it's great to like carry the units along here because you can really see it then. I'm going to have 785 divided by 120. And I'm going to find to the nearest hundredth of a gram per cubic centimeter, 6.54. You can just see those units. There they are, grams per cubic centimeter. All right. Various substances, right, rocks, metals, air, liquids, they all have different densities, a different amount of grams that fit inside a cubic centimeter or a cubic foot or whatever. Let's take a look at 2 more situations with mass density. All right, letter B. We've got a mass of 751 grams inside of a sphere whose radius is 6 centimeters. All right, well, what I'd like you to do is try to figure out what the density is here. And, right, even though we just looked at volumes of spheres, let me write down the volume formula for a sphere just to get you started. That's going to be 4/3 pi r cubed, right? First thing you're going to want to do is figure out the volume of this sphere, then divide the mass by that volume to come up with the density. Pause the video now and go ahead and see if you can find the density within this sphere. All right, well, first things first, let's get that volume, right? So that's going to be 4/3 pi times 6 cubed. Again, be careful, make sure to have the pi, make sure to have the cubed, all that kind of stuff. So we've got our fraction, still not, let's try it again, 4/3 times pi times 6 to the third. There's our volume. That is 904. I think I'll take it a couple decimal places. 0.78 cubic centimeters. All right. So that's where you have to start, right? 904.78 cubic centimeters. And now my density is just going to be my mass divided by my volume. So that's going to be 900, that's going to be 751 grams. I almost did it the other way around. Divided by 904.78 cubic centimeters. And let's see what that's equal to the nearest hundredth. We've got 751 divided by 904.78, and that's going to give us 0.83, grams per cubic centimeter. All right. And we've got one more involving a cone. And if nothing else, these are great problems to give you a little bit of work in calculating volumes of various figures. Again, let me get you started with this, right? With a cone, the volume is going to be 1/3 pi r squared times h. All right, so start off with that and see if you can figure out the density of the mass that lies within that cone. All right, let's do it. Again, a little bit messy because we've got the 1/3 and the pi. All right, our r is 2, so it's going to be 1/3 times pi times 2 squared times 8. Let's figure out that volume of the cone. Again, let me just clear this out. Let's go with our fraction. 1/3 times pi times 2 squared times 8. 1/3 pi r squared h. That's going to be 33.51 cubic centimeters. All right. And now our density, which is going to be our mass divided by our volume, is going to be 93 grams divided by 33.51 cubic centimeters. All right, so I'm going to just take my answer, or not my answer, but I'm going to do 93 divided by 33.51. Nope. 0.51, that's a little bit better. And I'll get 2.78 grams per cubic centimeter. Okay. Now, just as a little side note, right, let's do exercise 4, which I love. Take a look. Water has a density of 1 gram per cubic centimeter, exactly 1 gram per cubic centimeter. An object will float in water if it has a mass density less than that of water. Would any of the objects in exercise number 3 float? Right? And this is kind of cool, right? Certain things float and certain things sink. And it's all about whether or not their density is greater than water's density or less than water's density. Water has a density of 1 gram per cubic centimeter. Any of those things up above float? Well, pause the video now and see if any of them do. And yeah, one of them does, right? Now don't get me wrong, 2 of them sink and sink quick, right? 6.54 grams per cubic centimeter, that thing's gonna sink, right? And so will our 2.78 grams per cubic centimeter. But that sphere, who knows, maybe it's a beach ball, I don't know what it is, but that sphere at 0.83 grams per cubic centimeter, that's gonna float, right? Whoop, the sphere will float because 0.83 grams per cubic centimeter is less than 1 gram per cubic centimeter. Lighter things will float in heavier things, especially when you're talking about gases and liquids. All right, let's keep going. One final problem, exercise number 5. A salad dressing recipe calls for 225 grams of vinegar and 150 grams of olive oil. Maria doesn't have a scale, but she does have a measuring cup marked in milliliters. Maria knows that the density of vinegar is 1.05 grams per milliliter, and the density of olive oil is 0.9 grams per milliliter. Determine the volume of vinegar and oil Maria needs for the recipe. Round your answers to the nearest milliliter. I'm sorry, not millimeter, milliliter. 1,000th of a liter. By the way, just as a side note, right, a milliliter, which is oftentimes used in cooking and other types of volume work, is exactly the same as 1 cubic centimeter. 1 milliliter and 1 cubic centimeter are the same thing. We don't need to know that for this problem. But what we do need to think about in this problem, right, is we've got masses of both vinegar and of olive oil, and we've got mass densities. What we don't know now is what the volumes are, and that's what we want to figure out. Pause the video now and see if you can figure out the volume of vinegar and the volume of olive oil that we need to add to make this recipe work. Well, this is rather cool. And take a look at something, right? Without putting any of the numbers up, right? Density is mass divided by volume. Right? That's what density is. But this time what I'm trying to solve for is the volume. Now, I can do that without putting any numbers in by multiplying both sides of this equation by the volume, which now tells me that the mass is equal to the volume times the density, which makes a lot of sense, right? If I have a density in grams per milliliter and I multiply it by how many milliliters I have, then I get how many grams I have. But I can now solve this by dividing both sides by the density, and I get that the volume is equal to the mass divided by the density, which is kind of amazing, right? The density equals the mass divided by the volume, and the volume equals the mass divided by the density. So, if I want the volume of the vinegar, I just need to take the mass of the vinegar, which is 225 grams, and divide it by its density, which is 1.05 grams per milliliter. And what will I get? Let's see, 225 divided by 1.05, and I'll find that I need to have 214 milliliters of vinegar. Okay? And likewise, right, if I want the volume of my olive oil, that's going to be the mass of my olive oil, 150 grams, divided by its density, which is 0.92 grams per milliliter. We now get, let's see, 150 divided by 0.92, we get 163 milliliters of olive oil. All right. Now, if you've ever had a vinaigrette dressing, right, and that is basically a dressing that mixes vinegar with almost equal parts olive oil, they're not too far apart, right, and you shake that up and let it sit, eventually what happens is that the oil floats to the top. Letter B. Maria shakes the oil and vinegar together in a jar. Eventually, the oil rises to the top of the container. Why do you think this happens? Pause the video now and let me know what you think. Well, this gets back to our last problem about which one of those things is going to float in water. The plain fact is, right, the oil is going to rise to the top because it's got a lower density than the vinegar. Anything that is less dense, when we mix two liquids together, will float to the top, and anything that's more dense will sink to the bottom. Side note, if you've ever heard the phrase that warm air rises, that is because warmer air is less dense than colder air. So if we mix warm air and cold air together, the warm air will float to the top, whereas the cold air will sink to the bottom. All right, so this happens because the density of oil, or I should say olive oil, is less than the density of vinegar. All right, so let's wrap this up. Now in today's lesson, forgetting about making salad dressings, right? We really worked with density. And density to me is a very simple idea and a very important idea. But it all basically boils down to division. When we divide two quantities, we're really always finding out how much of the numerator sits within a unit quantity of the denominator. Now for us, that mainly boils down to dividing populations by area to find out population density, and dividing mass by volume, giving us what's called mass density, right? So in one case, we're talking about how many people live per square mile. In the other case, we're talking about how many grams are in a cubic centimeter or a cubic foot or something like that. Density is an amazingly important idea in science. It comes up all the time, not just in science, math, economics, all over the place. Anytime you want to know how much of one thing sits inside of another thing, you're really talking about density. All right, and we'll see a little bit more of it in our next lesson. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.